I'm gonna just give a brief overview again, similarly to what I said on Monday about WarpX. It's an open source particle in cell code for plasma physics simulations in general and interactions of plasmas with laser beams and particle beams. It's built on AMReX and it's running on CPUs and all sort of GPUs thanks to AMReX. There's a relatively active community of developers and contributors in general since 2017, when this started basically with the exascale computing project. And we always mention that we were awarded the Gordon Bell Prize 3 years ago for some mesh refinement simulations of laser-driven electron acceleration, collaborating with the AMReX team as well as some collaborators in Europe and Japan. So in this talk, I'm gonna give like a few updates about what's been new since the end of the exascale computing project as far as WarpX goes. And the goal would be to like essentially give examples of how the workflow goes. So we have some new applications and new physics areas that we're interested in, and this is leading to some new developments on the AMReX end. And I want to just emphasize and echo what was said this morning about the fact that there is a very synergistic approach to this from the AMReX end, and it's essentially possible to really upstream some of the development for solvers and such things, so that we essentially get the best out of it when it's driven by the new physics applications that you're interested in. So we started by being focused on laser plasma interactions for wake field accelerators, which is like a particular type of particle accelerator. And we're now looking into some more physics applications, such as beam-beam interactions for collider physics and some fusion modeling and simulation, especially inertial fusion. We have expanded a bit the collaborations with the national labs and the fusion industry partners. And this is essentially what I'm going to talk about in terms of the type of development that's been driven. There's only one slide before that about like a relatively major upgrade that we did in our code. I think towards the end of ECP and going farther, which was about transitioning our WarpX particle container, which is based on the AMReX one, to structure of arrays. And this we found out that this was beneficial for us. Here I'm quoting like the maximum speed up we got for I think only one kernel actually. In general, it was more like about a few percent speed ups. But this is something that happened. I think Andrew worked a lot on this together with Axel Hübel. And this is an example of something that essentially we got some relatively good speed up, for kind of free after interacting with the AMReX team and following, essentially leveraging the infrastructure that they provide. So one first application is collider physics and beam-beam interactions. So we want to model beam-beam effect. So what happens when two particle beams collide with each other to guide essentially the design of future particle colliders, things such as like the so-called Higgs factories. So, facilities where you can have a lot of events where Higgs bosons are produced and so on. And we want to understand the physics of the beam-beam interactions because it's critical to then measure some of the quantities that guide the design of these facilities. These are like multi-billion, trillion-dollar facilities, so you definitely want to have some predictive capability from simulations before going and just choosing a design or choosing a particular set of parameters. This required, of course, the development of some new physics, such as like new quantum electrodynamics processes in the code for like collisions of particles and such things. And it also led to some algorithmic developments. In particular, we have a situation with typically two beams that are propagating and going towards each other before colliding. These are like ultra-relativistic beams. They are very anisotropic. They are flattened, and they have extreme aspect ratios. And essentially, we want to compute the self-fields of these beams through Poisson equation, using open boundary conditions and taking into account again the anisotropy of the beams. And it turned out that we required a different type of method than the standard like MLMG solvers that were available in AMReX. And this led to the implementation of a solver based on the convolution method, where you basically take a Green's function, you compute the convolution with like the source distribution function, and then you take advantage of the fact that the convolution can become like a simple product in Fourier space. And so what happened is that on the AMReX end, we had a new FFT-based Poisson solver implemented primarily by Wei Chun, I think, and where you can essentially, yes, from the user perspective, you can pass in a green function of your choice, and then you can use this solver to have some more correct and accurate results for a case like this one with again open boundary conditions and anisotropic beams. I apologize for the plots. This is like stuff I got from some other slides, but essentially like it's supposed to be showing that on the left you have some fields that don't really look like they are correct, and then they are obtained with the MLMG solver, and then you have on the right the IGF, the integrated green function solver, which improves the accuracy of the result and the correctness of the result, and also on top of like the method itself based on Green's functions. Initially, there was an implementation that was only serial. Then it became a parallel implementation based on Hefty. And then we ended up, I think, requesting like the usage of the AMReX on FFT infrastructure, which turned out to be faster than the FT one, and that's again something that happened as algorithmic development on the AMReX end. So you now have an FFT-based Poisson solver, which I think didn't exist before. This application led to the development of these. So for inertial fusion, just quickly, here we're looking at the main point I want to make here is that we're looking at a problem with a very wide range of time scales, and we needed to essentially go about implementing an implicit time solver to be able to take large time steps and not be constrained by the smallest time step that we need to resolve in order to do these simulations. We have some fast kinetic scales of the plasmas, and then we have some slower fluid-like scales for what happens when the fuel that is contained in the capsule in the middle of that cylinder is essentially compressing and expanding. And so we had the need to implement an implicit infrastructure to solve this, to go start doing simulations for this problem. And that infrastructure was actually implemented mostly by our colleagues in Lawrence Livermore lab. But what I want to mention here is that the implicit infrastructure for sure is much more complex than the simple explicit time integration. It involves nonlinear solvers. It involves linear iterations within those nonlinear solvers, and sometimes you need to also apply preconditioners when you're at the linear stage. to make it essentially faster to converge the solution. So what this led to was the following. We have a new linear solver for the linear iterations within the biggest nonlinear scheme, which is a GMRS solver. My understanding is that AMReX already had like an interface for the GMRS solver provided by the Hyper library from Livermore, but this was actually implemented as its own in-house solver. Again, I think primarily by Wei Chun. And then another thing that that happened related to this is that there was an additional preconditioner added for a particular like kind of equation, which involves the operator curl of curl. So when we write down this implicit model, we end up with an equation that involves like the curl of a coefficient times the curl of E plus a linear like a linear term like coefficient times E, and then equal right hand side. And so as a result of this, there is also a new curl solver available in AMReX that takes care of that. And we're trying to like orchestrate all of this together. So apply the preconditioner and then use the GMRS solver and then put that into the nonlinear bigger infrastructure, which is I think the one that is called PSJFNK, which stands for like particle suppressed Jacobian free Newton Krylov. Like it's a method that is described in one of the papers of our collaborators, like recent papers from Justin Angus and in Livermore lab, and I can for sure like give references. You find those references as well in the documentation of WarpX, because this is now in the main branch. So what I want to mention, going a bit farther and not staying too technical, is that as I was saying, like there's a two-way partnership with AMReX. We were able to upstream some of the the development on the algorithmic side to the AMReX team. The way we work is that we collaborate on a weekly basis with them. We co-organize typically now, I would say, on a yearly basis hackathons where essentially the WarpX core developers work together with the AMReX developers and work on like major upgrades, major developments that are needed and that need a little bit more of coordination rather than the usual asynchronous GitHub work. And in terms of, I want to mention a few points in terms of like looking ahead and also a few sort of open questions. Of course, on the technical side, we have these new solvers. They can be improved, they can be further optimized, they can have better scaling. We need all of those things because we need to be able to run like large-scale simulations that are robust and fast when we want to, for example, scan a large number of parameters when it comes to being predictive for design of accelerators, for instance. But the point I want to mention is more like on the way we work side of things. Again, the partnership is strong and it's working effectively. I think there is a way to think about improvements when it comes to sort of what I call knowledge transfer, in the sense that we depend very much on the in-house expertise and knowledge that is in the AMReX team. I think a lot of questions from WarpX developers and users, especially new developers, come recurrently, and they need to be addressed always following the same workflow of like typically reaching out to someone in AMReX and like, okay, can you remind us like how this works? Because these are very complex code bases, both WarpX and AMReX, as you all know. And so I'm wondering if there's some ways to sort of freeze some of the knowledge that is existing in the AMReX team beyond what can be accessed in documentation, for instance, and sort of pass it down to the application teams, so that there is a bit more of like synergistic work and a bit more of like knowledge base on the application end, for us to be able to sometimes understand bugs, fix bugs and so on more easily than just always necessarily only depending on someone from AMReX beyond. So I'm thinking also about like whether there is a way, for example, to make the documentations of the two codes sort of flow as a one single, flow of information, rather than more like a situation where you have to jump between one and the other, and not necessarily easily avoid getting lost, essentially. So I think this is something that it's coming up a little bit from time to time, and I think it could be worth thinking about it, brainstorming a little bit, and I can discuss more like in person if you're interested. That's it. So the main message was that WarpX was eager to look at new physics applications because we need it for essentially being able to sustain ourselves. Funding decides typically, what areas are of high priority or like mid priority, and we need to be able to follow that to continue existing. We have a code that is very capable of handling a large variety of physics application because it's a general plasma physics code, and plasmas are ubiquitous, so you can sort of design it in a way that can be used for different applications. And this led to algorithmic developments in the AMReX space. And the hope is that those new solvers are now available for everyone that is using AMReX. So if people are here in this room that already use AMReX and they may think like, actually we have an equation that looks similar and we might want to use that same solver, or people who are thinking about using AMReX and see the kind of way that you can work together as two teams. I hope that's helpful, essentially. And that's it. If people are interested in discussing more technical details, I would encourage to like reach out through either GitHub or Slack. We have a very active Slack workspace where you can reach out to the whole WarpX team. Again, it's a complex code. If you ask one question to one person about any point, any component of the code, you're not likely to necessarily get the answer, because not everyone knows every single piece of the code. It's a complex code base. So the best way to find information is either go to the documentation and tell us that you didn't find what you were looking for, so that we can add it. And then otherwise, like reach out and to the broad developer team and see how we can find the information that you need, essentially. That's it. Sorry.
We have time for maybe one question while the speakers are changing over.
Yeah. I have a question about you had obviously one of the what this was converting from structs, an array of structs to structural array. How difficult was that transition for you?
How difficult was it? So I think it took a while. I didn't really work on that. I think other people did that work. Andrew and Axel, you mostly interacted with each other.
Yeah, I think that, so this was removing a limitation from AMReX that the particle decisions and IDs specifically had to be array of structs. And everything else could have been structured arrays in the beginning. I hope that now that those changes are made in AMReX, it's not that hard to transition in an application code now.
Yeah.
But yeah, there are a lot of internal changes. All right, let's take Edoardo again.